Welcome back. We are going to continue talking about proximal point algorithm in the primal and in the dual. And in particular, we're going to talk about different interpretations of both of these algorithms and use that as an excuse to introduce some concepts like smoothing and the Moreau envelope. So let me write down again where we are. We're thinking about in the primal. If we're going to stay there, we can just write a single minimization problem like this, and recall that the proximal point algorithm, which is not proximal gradient, is simply the iteration xt plus 1 is the prox of lambda f of xt. And we've seen this, we saw a number of properties of this. So one thing that we saw is that we can write this using the resolvent, which is something that we defined in the previous lecture in this series on proximal point algorithms. So we saw that xt plus 1 can be written as being I plus lambda subdifferential of f inverse of xt. And therefore this makes the proximal point algorithm a backwards algorithm. If we write this out, it becomes an implicit algorithm, and it looks very similar to gradient descent except for that implicit aspect. So gradient descent is a forward operator, proximal point algorithm is a backwards operator. And so we studied a number of its properties in the primal, and then also looked at it in the dual. So remember, if the primal is, let's write it in our more general exploitable form of minimizing f of x plus g of ax, then the dual is maximizing minus f star of minus a transpose z minus g star of z. And the proximal point algorithm in the dual is minimizing an augmented Lagrangian in the primal. In the dual is the augmented Lagrangian method, or ALM, in the primal. And specifically what this means, and again, see the previous lecture in this series to see the details, is that zt plus 1 can be defined as zt plus lambda ax hat minus y hat, where x hat and y hat are the solutions to the augmented Lagrangian problem, which is f of x plus g of y plus the usual Lagrangian term, zt transpose ax minus y. And if we were to stop here, note that this problem would completely decouple. And in fact, that's what we have when we have gradient ascent. And we've also talked about that in this series. But we have the additional term, which is the augmented Lagrangian term, of the squared norm of ax minus y squared. So this is where we are. And now I want to move to interpreting the proximal point algorithm in the primal and also the augmented Lagrangian in the dual, and therefore establishing some more of its properties. But also, as I mentioned, it's a great excuse for us to introduce some other important notions that are very useful in convex analysis and convex optimization. The first thing I want to introduce is a concept called Moreau-Yosida smoothing. We have talked about when we first introduced the Fenchel transform, we talked about this duality between addition in the dual and infinitesimal convolution in the primal. And this very much relates to Moreau-Yosida smoothing. So first, let's define the definition. If f is a function, doesn't have to be doesn't have to be smooth, and note that I'm not making any assumptions about it. Then its Moreau envelope is defined as follows. And note the notation. So f subscript, I'll write this in parentheses, lambda, of x is defined as the infimum over u of f of u plus 1 over 2 lambda times u minus x squared. And this is sometimes called Moreau-Yosida regularization. And you'll note that this is exactly equal to what we had defined as infemal convolution. So this is just the infemal convolution of the two functions f and squared norm divided by 2 lambda. Of the functions f and the function squared norm divided by 2 lambda. This is equal to the infimum over all u plus v whose sum is equal to x of f of u plus 1 over 2 lambda times norm squared of v. Nothing has happened here. I'm just relating it to specific definitions that we've made in the past. And note that we can also write that f lambda of x is equal to f of prox lambda f of x plus 1 over 2 lambda times of the norm of prox lambda f of x minus x. Again, nothing has happened here. I've just observed that the Moreau-Yosida smoothing is a function, and it's just an evaluation at the point which is equal to the prox operator. So this is really all I've done. I just observed that the infimizer here is in fact the prox operator. And so I just took that as the definition, and then I plugged it back into the definition of I plugged it back in for u. This is the basic definition that we're gonna work with. So let's try to understand some of the properties of this Moreau envelope. So first of all, let's look at what its conjugate is. Conjugate of the Moreau envelope. And remember this fact that I mentioned, and you can find this in the series on the Fenchel transform, that the conjugate maps infemal convolution to addition in the dual. Infemal convolution to a sum. In other words, if we have f is equal to f1, the infemal convolution of f1 and f2, then the Fenchel conjugate is equal to the Fenchel conjugate of f1 plus the Fenchel conjugate of f2. And so for us, this means that the conjugate of the Moreau envelope, or f lambda, its conjugate, is equal to f star of y plus whatever the conjugate is of the 2 norm. You should be able to do this calculation. It's just equal to lambda over 2 of itself squared. So in this sense, you can check that the 2 norm is self-conjugate. And remember, we actually derived something more general when we looked at when we computed the Fenchel transform of a quadratic function. So what are some properties? First, we can see that immediately that f lambda of x is convex because it is the infimum over u of a function which I'll just write as f of x comma u. What is this function? This is just f of x plus, you're just looking plus 1 over 2 lambda times x minus u squared. Note that this function f of xu is jointly convex in both x and in u. And therefore, if I take the infimum over one of its arguments, then the result is convex. Note that this is a different argument from our usual argument that the maximum of convex functions is convex. Here we have the minimum. So just generically, if I can't apply that argument, so we need to be a little bit careful here in x and u. So I'll leave this as an exercise for you to show that this is in general true. The exercise is to show convexity in this general setting. That's one basic property. So if as long as f is convex, then its Moreau envelope is also convex. And then, regardless of smoothness of f, its Moreau envelope is smooth, which is also why it's called Moreau-Yosida smoothing. F of x is smooth. So let's think for a minute, how can we see this? Well, one simple argument is, again, drawing from the work that we did on studying properties of the Fenchel transform. And here we see that the Moreau envelope is the Fenchel transform of this function here. And what is this function? F star is always convex, and F star plus a norm is therefore going to be strongly convex. And therefore the Moreau-Yosida envelope is the Fenchel transform of a strongly convex function. And we talked about how, and in fact derived, how strong convexity and smoothness are therefore dual properties of each other. So let's see a few examples of what this operation does of smoothing, of taking the Moreau envelope. So first example we might try is the indicator function. So remember something like this. The indicator function, say, of an interval, its epigraph might look like something like this. So let's take f of x equal the indicator function of some convex function, some convex set of x. So then the smoothing of f becomes a distance function to the set. 1 over 2 lambda times the distance of x to x squared. So basically, it would be something like, in this case, in this simple one-dimensional case, a quadratic. So again, it's going to be 0 when you're in the set, distance is 0, and then it grows quadratically outside. Again, I'll leave this for you to check. I'll try this as an exercise. Another non-smooth function that we've seen is the L1 norm, the sum of the absolute values of xi, or just the 1 norm. And in this case, again, I'll leave this for you to check this calculation. The smoothing of x is equal to the sum of not absolute values, but the individual smooth terms of absolute values, and it's something that is called the Huber function, or the Huber penalty sometimes. Very useful in machine learning, and in particular in robust statistics. So this is equal to, I'll write these definitions in a minute. Oops. H lambda of xi, where h lambda is a univariate function, and it's simply equal to z squared over 2 lambda when z is less than lambda, and it's equal to z minus lambda over 2 when z is greater than lambda. And you can parse this algebraic definition, but basically what this looks like is it says that it grows. So here's a quadratic, and what this does is it matches the quadratic up to a particular point, and then it grows linearly. So it's quadratic near the origin, and then it has linear growth. This is used in robust statistics, for example, in robust regression, if you don't want to pay too much attention to outliers. So you don't want to weigh them. You don't want to weigh them too much, but still, you may want the benefit of having the behavior of a least squares like regression when for your non-outliers. So now let's look at what the gradient of the Moreau envelope is. And it's natural because then we might ask, what does gradient descent on this smoothed function look like? So we know that we just saw in the previous slide that this is a natural way to smooth. And we like smooth things because we can run accelerated algorithms. And in addition, if something is smoothed, we know that gradient descent is going to converge faster than the subgradient method. So this is a natural idea to try to smooth and then either run gradient descent or accelerated gradient descent. So again, writing down what we have, f of f lambda of x is equal to the infimum over u of f of u plus 1 over 2 lambda u minus x. What do we know so far about it? First of all, and we're assuming throughout that f is initially convex, so we're starting out with a convex function. So so we know that, as we just saw, that f of lambda is convex because f is, and smooth. And furthermore, you can check that if f is closed, then f of lambda is closed. And in particular, that means that it is that the dual of the dual is itself. So this means that f of lambda is now closed and convex. So f of lambda of x is equal to f lambda, the dual of the dual, evaluated at x. And just writing out the definition, this is the supremum over y of x transpose y minus f star of y plus lambda over 2 times y squared. And taking the derivative of this to see what is an optimizer of the supremum, we find that x minus lambda y is an element of the subdifferential of f star of y if and only if again using the inverse property of differential dual, of the gradient or subdifferential differential dual, y is an element of the subdifferential of f at x minus lambda y. By strong convexity of the dual, we know that the maximizer is unique. So the maximizer in the dual is unique by strong convexity. And again, this means that the primal is differentiable. And moreover, we know that therefore y hat is equal to the gradient of the Moreau envelope of f at x hat. And you can check this, that this implies that this in turn is equal to 1 over lambda times x star minus prox lambda f of x hat, which in turn is equal to prox of 1 over lambda times f star of x hat over lambda. So this, we know it holds by something that we showed that actually has the same name. It's called the Moreau decomposition. Remember, this says that for any point x, x is equal to prox f of x plus prox f star of x. It's a generalization of orthogonal projection. Okay, so this gives us an idea of what the gradient of the Moreau envelope looks like. So now we can look at what gradient descent looks like. And the connection we're going to make is that, in fact, this is just the proximal point algorithm. So again, f lambda of x is equal to the infimum over u of f of u plus 1 over 2 lambda x minus u squared. I want to do gradient descent. Gradient descent tells me that xt plus 1 is equal to xt minus lambda times the gradient of f lambda at xt. And now I'm just going to plug in what I had on the previous slide. This is equal to xt minus lambda times 1 over lambda times xt minus prox lambda f of xt. This is the first equality at the bottom of the page. And just multiplying out, we see that indeed this is just equal to the prox of xt. So immediately we see that the proximal point algorithm is just gradient descent on a smoothed version of f. This is yet another relationship between the proximal point algorithm and gradient descent. Remember, we had also seen that as long as lambda is very small, then proximal point is actually very close to gradient descent. So this also makes sense if we look at the definition of the Moreau envelope and think about what does it mean for lambda to be very small. What does it mean in terms of the smoothing that you get? Also, this immediately tells us something else that is interesting, which is that if we just minimize the Moreau envelope, we're going to get the same point as if we found the minimum of our original function. The minimizer of the Moreau envelope, the smooth function, is equal to the minimizer of our original function. This is useful separately because it basically means that if you want to smooth a function with the hope that you're going to get faster convergence, then you also know that you're converging to the right thing. So the minimizer of the smoothed version is the minimizer of the original. Okay, now let's turn back to the augmented Lagrangian and see what properties we have there. So remember the augmented Lagrangian method. I wrote it down in the first slide today. And the key step there is to solve x hat y hat is equal to the argmin over xy of f of x plus g of y plus the Lagrangian plus the augmented Lagrangian term, or we can equivalently write this by completing that square. And again, because we're looking at an argmin, we don't care about adding constants. This is equivalently equal to the argmin of this, where rather than having a Lagrangian and the augmented Lagrangian term, I'll just write it in one. Ax minus y plus z over lambda, all of this squared, and again then zt plus 1, this should be zt here, is equal to zt plus lambda ax hat minus y hat. And we saw in the previous lecture on this series that the augmented Lagrangian method is exactly applying the proximal point algorithm in the dual. But ALM is the proximal point algorithm in the dual. But we just learned that proximal point algorithm is a gradient descent on a smoothed function. In the dual, this would be gradient ascent on a smooth dual. So this is equal to gradient ascent on a smoothed dual, which again makes sense because of this duality of strong convexity and smoothness. So what is the augmented Lagrangian method doing? You can see that it's operating in the primal regime. It's looking over x and y, and it's minimizing f of x plus g of y, essentially what we had originally, plus this term, this quadratic term that's making it strongly convex. And so, and that exactly corresponds to running a gradient descent on a smoothed version. So if you just started with the augmented Lagrangian formulation and said, this is strongly convex, therefore I don't need to apply proximal point, I can just apply gradient ascent in the dual, you get back the proximal point algorithm for the original function. So this is the connection here. One other last thing. Note that we can also just define. We can also eliminate. We can eliminate y in the primal and consider this as just smoothing one of the functions, just smoothing g in particular. This corresponds to a smoothed g. So in other words, this leads to something like x hat equals argmin of, so specifically what I'm doing here is looking at this in the box, observe that y is only present in the last two terms, and so I could carry the minimization over to those last two terms and actually perform it. So what is the minimization going to be in those last two terms? That's a minimum of g of y plus a smoothing term. So this is what I mean by, we could think of this as minimizing f plus the Moreau envelope, or a Moreau-like envelope of the function g, so of a smooth version of g. So this is like writing x hat is the argmin of f of x, and it's only a min over x now, f of x plus, I'm no longer going to have g of y because I've performed that minimization. I have the Moreau envelope of g of y. Not exactly, because the quadratic term is, well, I have to put it exactly in the form of the Moreau envelope, and you'll see that that this looks like g of 1 over lambda, the smooth version at ax plus z over lambda. As an example of this, let's think about minimizing a function f of x plus a non-smooth term. This is one norm, so basically an absolute value. So then x hat in an augmented Lagrangian version of this is the argmin of f of x plus whatever the smoothed version is of ax minus b, one norm. And we already saw that the smoothed version of an L1 norm is this Huber loss function. So these are some other ways to see the proximal point algorithm in the primal and in the dual, and therefore also to understand the connection with the augmented Lagrangian.